This is Gubbi online classes for Ncert 10th standard and Cbse 10th standard mathematics and science classes. So today we are going to start with a very beautiful, important, enjoyable chapter in mathematics, in particularly geometry, that is similar triangles. So it's a very important chapter. I enjoyed like anything, but the condition is you have to listen very carefully. Second condition is you have to practice each and every problem the day itself. Third condition is you have to write the unit test or the concept wise test which is given to you regularly. Fourth condition is you should be conditioned to correct your mistakes there and then itself. If these are the conditions, you will enjoy the concept of similarity. Right. So in the previous classes of regarding triangles, we have come across we have learned many properties of triangles. So among them, one is, I hope you remember, S into S minus A into S minus B into S minus C, square root of this, that is A is equal to, I hope you remember this formula. So this formula is called Heron's formula to find the area of any triangle when the perimeter of the triangle is given. So that is S is equal to A plus B plus C. That is 2S is equal to A plus B plus C. So this was the Heron's formula in the previous classes you have learned. And after that you came across the congruency of triangles. In your 8th standard class in geometry, it was a very big chapter. You enjoyed a lot of postulates connected to congruency of triangles like ASA postulate, SAS postulate, SSS postulate, AA and RHS postulate. So all these postulates you enjoyed there, that is AAA. I hope this was not there. Okay. So all these four postulates you enjoyed it, and based on these postulates you also come across some enunciations where you proved logically these enunciations in the form of theorems. So logical proof for an enunciation. Enunciation is a statement in geometry where the truth of the statement can be verified by doing construction and measurement, and also the statement and our enunciation can be proved logically. So when we prove the truth of the given statement by doing construction and measurement, that becomes the skill in geometry. Whereas if you prove the truth in the enunciation through logical steps, that's called a theorem. So while proving an enunciation in a theorem, we use the axioms, what you have learned in your 8th standard class, postulates, enunciations, and you have come across simple theorems. So using the knowledge of all these, you will be proving the previous theorems. So that is the previous knowledge which is required. So usually in geometry we call them as lemmas. Before proving a theorem, the basic knowledge or the background knowledge required for proving a theorem is called as lemma. So before learning the similar triangles, better you go through your 8th standard congruency chapter, that is geometry chapter, congruency of triangles. Coming to 9th, just refer it. Just you fresh up with the statements connected to triangles. So saying, I'm going to repeat in the class, no doubt in that, but if you are knowing it earlier itself, it's a better situation. Right. So you come across congruency of triangles where every postulate or congruency was proved in the form of a theorem, and many riders and many identities were proved. So those problems which end with prove that problems. If so and so is there, so prove that this is that, something like that. We have come across those type of problems in geometry. So prove that problems in geometry, they are called as riders. So many riders you are going to come across in similar triangles. Prove that they are equivalent to that of theorems. They follow theorems. So problems which are like show that this is the thing, show that this, and you have come across in AP chapter also. So any problem ending with show that are called as identities. They are called identities. Okay, so we have theorems in this chapter. Some 3 to 4 theorems you are going to come across. Then prove that they are called riders. Then show that. So prove that problem. Show that problem that is riders and entities. They follow the theorems. So they are also true. If the enunciation in the theorem what we have proved is true, then this is also true. This is also true. So these are called riders and entities. Right. So apart from this, you will be having numerical problems. Some values of some variables will be given, and you will be asked to find out some other variable. So you are going to find out that variable, and you will get an answer in some numericals. So if that is the problem you are doing, then they are called as numericals. Right. So they are numericals. So in entire geometry, you will be having only these things. You will be having a theorem. Maybe you will be having its converse. So I will tell you what is a converse while doing theorem. So this is the theorem, its converse. Prove the problems, show that, and numericals. So this makes the syllabus of geometry. So like this, you will be having 3 to 4 theorems, 3 to 4 theorems, 3 to 4 their converses, 3 to 4 riders, some entities, and some numericals. So usually entire chapter is divided into some 4 big divisions. Theorem 1, its converse, its riders, its entities, numericals. Theorem 2, its converse, its entities, its riders, and then its numericals. So like that the chapter will be designed. So in your textbook some products are placed here and there somewhere. That is misplaced. So what we teachers do is, first we prove the theorem, then we go with the converse, then we go with the riders, then we go with entities, and then at last we go with numericals. So this is the psychological order in which you have to learn geometry. Right. So apart from this, you have learned maybe your physics teacher has taught you the mirror formula. So 1 by F is equal to 1 by U plus 1 by V. So do you know how it is derived? I hope you remember. He derived this formula, mirror formula, by using some concept related to similar triangles. I hope he has discussed with you. So he used similar properties of similar triangles to prove the relation between F, U and V. So more doubts regarding the concept derivation, please contact your physics teacher. Right. Okay. So we'll go with the next concept. So these are the previous things you have learned regarding triangles. Right. Now we'll go with a small imagination or a small story. Right. So imagine a school. Two students are called. Mathematics teacher calls his two students. You come here, right. Go there, go to the tree, measure the shadow of the tree. Measure the shadow of the tree. Right. For example, this is some tree over here. The student is asked to measure the shadow from here to here. The shadow is there somewhere here. He is asked to measure the length of this shadow. So the students uses the measuring tape, and he measures the distance of the shadow, that is length of the shadow. So this is, let us take it as length of the shadow, let us take it as S1, okay, length of the shadow S1. So he calls some other student, hey other student, you come here, do one thing. See, beside that tree there is a flagpole. You do one thing, you go and measure at the same time, not at the different time, at the same time. You go to the pole, measure the length of, that is, measure the length of the shadow of the pole. So this is the flagpole, usually in schools we have. So this is the flagpole. He tells him to measure the shadow of the pole. Okay, let us not take this. For accurate measurements, let us take this. So this is the length of the shadow. Okay, it's a short one, okay. So this is the length of the shadow what he has got. So let us take it as S2. And your mathematics teacher knows that the height of the pole is some 5 meters. Height of the pole is 5 meters. Now, see the logic behind this. You know the length of the shadow of the tree. You know the length of the shadow of the pole. You know the height of the pole. Using this value, and using this value, can you find out the height of the tree, that is h? Can you find out this? Can you find out the height of the tree? It's a very simple concept, right? So, you know the length of the shadow of the tree, you know the length of the shadow of the pole, and also you know the height of the pole, that is the teacher already knows earlier. So, using 1, 2, 3 elements, can you find out the height of the tree without using measuring tape? Without using measuring tape. How you can find out the height of the tree? Right? So here, if you want to find out the height of the tree without using the measuring tape, here you have to use the concept of similar triangles. So this is what you have to use, the concept of similar triangles. Using the same concept, the height of the pyramids were being used to find out in Egypt. Height of the pyramids. For example, this is a big pyramid, very big pyramid. So it is its shadow. This is the shadow of the pyramid. Let us take it as S1 like this same. At the same time, they used to keep some stick or something which is a bit lengthy one. Let the height of the stick be some 3 meters, and let the shadow of the stick be some 5 meters, something like that, right? So we were knowing this value, we were knowing this value, and we were knowing this value, that is both the shadow length we were knowing and the height of the stick we were knowing, and using that we used to find out the height of this pyramid, height of the pyramid, by using the concept of similarity of triangles. So this is the beauty of the concept, right? So before entering into the concept of similarity, first you have to know something about the size and shape of geometrical figures. So before knowing this, size and shape. Okay. When we come to size and shape of geometrical figures, that is plane figures. When we draw plane figures on geometrical figures on a plane, we give much concentration on shape and size. Shape, size, they are totally two different concepts, but they are related in this chapter, right? So we will discuss about the 3 possibilities of geometrical figures which can be drawn on a plane having different shape, different size. Case 1, we will take this. We will take case 1 as different shape, different size. So this is very important. This is very, very important. You have to concentrate. Different shape, different size. Okay. I have a rectangle. I will call it as a rectangle ABCD. This is a rectangle ABCD. So here opposite sides are equal, we know that, and all the 4 angles are equal to 90 degrees. You have studied in your 8th standard geometry. And I am having another geometrical figure. Right. So this is PQRS. Let us name the vertices. So here all the 4 sides are equal. This angle is equal to this, and this angle is equal to this. So I can call it as a rhombus. So here this is a rectangle. This is a rectangle, and this is a rhombus. So here when you compare these 2 geometrical figures, plane figures, we see that they have different shape. Totally they have different shapes, right? And they have different size also. So this is one of the possibility of 2 geometrical figures which can be drawn on a plane. Different shape, different size. Okay, we'll go with case 2. Case 2. Same shape, same size. Same shape, same size. will take up two triangles. Okay, this is triangle ABC, and I'll take another triangle. This is triangle PQ. Right. When you compare these two triangles, you can see that they have the same shape, and they have the same size. So in your previous classes you have learned that two geometrical figures having the same shape and same size are called congruent figures. They can be called as congruent figures. So when does two geometrical figures becomes congruent? When they become congruent? Without twisting or bending. Without twisting or bending. Without squeezing or without enlarging. Without twisting or bending. Without enlarging or without squeezing it. When you keep one geometrical figure on the other, and if they fit exactly, then those two geometrical figures can be called as congruent. See, this is the most beautiful basic which is required for learning similar triangles, right? Without twisting or bending or squeezing or enlarging. If you place one geometrical figure on the other, see, if I pick this geometrical figure from here, if I place it on this side fits on this exactly, this side fits on this exactly, this side fits on this side exactly, this angle will be equal to this angle, this angle will be equal to this angle, and this angle will be equal to this angle. So, without bending or twisting or enlarging or squeezing, if one geometrical figure is placed on other, or if you place this on this, if they fit exactly, that's called superposition. If you superimpose, if you pick out this and superimpose on this, and if they fit exactly, then those two geometrical figures are said to be congruent. So why they fit exactly? Why they look? That's what the concept what I am discussing here. Why they look same shape? When we see through our eyes, we see that they have the same shape. Why they look the same shape? Here, same shape depends upon the angles. Same shape depends upon the angles. So this angle will be equal to this. This angle will be equal to this, and this angle will be equal to this angle. If in both the geometrical figures, if they have their corresponding angles, they are called as corresponding angles. When you take out this geometrical figure and place on this, if you take out like this and place something like this, it won't fit. It won't fit. If you take out the geometrical figure, fit on this, the vertex on which the other vertex lies, they become the corresponding angles. This vertex lies on this, therefore this angle will be equal to this. This vertex lies on this, therefore these angles will be equal. So, they are called as corresponding angles. Simple definition for corresponding angles is equal angles are called corresponding angles. Very simple. Equal angles are called as corresponding angles. So, this is equal to this, therefore corresponding. This is equal to this, corresponding. This is equal to this, corresponding. As the internal angles, three internal angles are there for this triangle. Three internal angles are there for this triangle. So, these three internal angles, that is corresponding three internal angles are equal, therefore they look same shape. How come size? How come they look the same size to our eyes? See, when we look at these two geometrical figures, our eyes, unknowingly to us, we do not know what our eyes are doing, unknowingly they measure the corresponding angles in a fraction of a second. Fraction of a second they measure these angles, and our eyes sends the information to the brain. Yes, all the corresponding angles are equal, they are same. So suddenly you tell, sir, they have same shape. But what makes them to get the same size? To get the same size, AB and PR are corresponding sides, because this angle is equal to this angle. Therefore, the side opposite to this and the side opposite to this are corresponding sides. If they are corresponding angles, the sides opposite to the corresponding angles are corresponding sides. For example, these two are corresponding angles. The sides opposite to this are AC and PR. Therefore, they are corresponding sides. The sides opposite to corresponding angles are called corresponding sides. So, if I measure AB, let it be 3 centimeters, and if I measure PR, it will also be 3 centimeters. If I measure BC, it will be 5 centimeter, and if I measure RQ, it will be 5 centimeter. If I measure AC, this will be 6 centimeter, and if I measure PQ, this will also be 6 centimeter. Now, when you take the ratio, when you compare the length of the corresponding sides, that is AB is to PR ratio, when you take, that ratio will be equal to 1:1. You can see that is AB is to PR is nothing but AB by PR is equal to 3/3. This cancels, it's 1:1. Similarly, BC is to RQ. BC is the corresponding side for RQ, and RQ is the corresponding side for BC. Right? BC is to RQ will take the ratio. So BC is to RQ is equal to BC by RQ is equal to 5/5. It cancels, 1:1. Take the ratio between AC and PQ, that is AC is to PQ is equal to AC by PQ is equal to 6/6. It cancels, that is again 1:1. So, why these two geometrical figures, when we see, it appears they have same shape and same size. Both the geometrical figures appears same shape because the internal angles of the first figure are equal to the corresponding angles of the second figure. Therefore, they look same shape. Why do they get the same size? Because when we take the ratio between their corresponding sides, the ratio will be exactly equal to 1:1, 1:1 and 1:1. Therefore, they appear they are having the same size. So, corresponding sides ratio is 1:1, compulsory. So, maybe for these two 1:1, these two 1:1, for this let it be sir 1:2. No. No. If that happens, they may lose the property of same size and same shape. They may not be congruent. So, if the two geometrical figures has to be congruent, their corresponding angle should be equal and the corresponding sides ratio should be equal to compulsory 1:1. If this is the thing, both the geometrical figures are said to be congruent. Right? Okay. Let us go with case 3. Case 3. Let us take a triangle. I'll take a triangle. I'll call it as triangle ABC. I'll take another triangle. Okay. I'll call it as triangle PQR. Right. I have two triangles here. Different shape, different size. Same shape, same size. Same shape, different size. Okay, same shape, different size. So, case 3. So, you can answer me why they have same shape. If I ask you, why these two triangles have same shape? Sir, these two triangles have same shape because their corresponding angles are equal. Okay, so this angle is equal to this because they are corresponding angles. This angle is equal to this because they are corresponding angles, and this angle is equal to this, therefore they are corresponding angles. Okay, as their corresponding angles are equal, therefore they are having same shape, but they are looking different. They are different in size. Why they are looking different in size? They are looking different in size because the ratio between their corresponding sides is not maybe 1:1. It's not 1:1. It's not 1:1. For example, this is an equilateral triangle. Let us take 3 centimeter. This is 3 centimeter, and this is 3 centimeter. This is 6 centimeters. This is 6 centimeters, and this is 6 centimeters. Let us take the ratio. AB is to PQ, 3 is to 6, 1 is to 2. BC is to QR, 3 is to 6, 1 is to 2. AC is to PR, 3 is to 6, 1 is to 2. So, the ratio between the corresponding sides is not 1:1. If they were 1:1, no doubt they were congruent figures. But as the ratio is not 1:1 and something else, therefore they are called similar figures. They are called similar figures. So these two triangles are similar figures. Similar figures. For example, if I take it as 9 centimeter, 9 centimeter, and 9, so it is AB is to PQ is 3 is to 9, that is 1 is to 3, 1 is to 3, and 1 is to 3. Ratio changes, but they are having the same shape but different sizes. So same shape, different sizes, geometrical figures are called similar figures. So for a simple definition of similarity, we can do one thing. Figures, geometrical figures having same shape but irrespective of sizes. Irrespective of sizes. For example, I can take a triangle like this, a very big one triangle with 100 centimeters or 300, 300 and 300. Take the ratio 3 is to 100, 3 is to 100 and 3 is to 100. So that becomes 1:100 ratio. Let it be, they are still similar. So the basic definition for similar figures is if they have the same shape and any different sizes they are called similar figures. They are called similar figures. But compulsory they should have the same shape. Let the sizes be different. No problem. Right? Okay. We'll go with the next concept. There are some similar figures which are always similar. See, in case of these two triangles, they are congruent. And the corresponding size ratio is 1:1. Here, they are having the same corresponding angles, therefore they have the same shape. So their corresponding sides is not 1:1, but something other than 1:1. Therefore they are similar. Right. There are certain figures in geometry where they are always similar. For example, if you take two circles, this is a circle of radius R1 and this is a circle of radius R2. So when you see these two geometrical figures, two circles are always similar. See, they have R1, it is R2 ratio. When you take the ratio between this radius, they are different. They have the same shape. But different sizes. Therefore, two circles, we say they are always similar. Right? Next, another example I have is example 1. Let us go with example 2. Let us take a square. All 4 sides are equal. I will take another square. In this square also all 4 sides are equal. Okay. In case of 2 squares, they have the same shape but different sizes. So take any 2 squares, any 2 different squares, they will be having the same shape but different sizes. Therefore, 2 squares are always similar. 2 circles are always similar. 2 squares are always similar. Okay. I have another example. Let us take a triangle. Let us take another triangle like this. It is triangle ABC. This is triangle PQR. Okay. This side is equal to this. This side is equal to this. And this side is equal to this. And this is 60 degrees. This is also 60 degrees. This is 60 degrees. This is 60 degrees. This is 60 degrees. And also this is 60 degrees. So what type of triangles are triangle ABC and triangle PQR? Both are equilateral triangles. Both are equilateral triangles. Okay. I will take another triangle. Okay, I will call it as DEF. This is 60 degrees. This is 60 and this is 60. Right. So when you compare this and this, they have the same shape but different size. Compare this and this, they have the same shape but different size. So therefore, 2 equilateral triangles are always similar. So 3 geometrical figures are always similar. One is circles are always similar, 2 circles are always similar, 2 squares are always similar, and 2 equilateral triangles are always similar. Right. So until now, what we have done, okay, this is a circle I am having here, this is another circle. I want to make this circle as this. So I will reduce this like this from all sides. When I reduce this, it becomes like this. So where they are congruent. One can be taken out and superimposed on the other. Now I want to make this figure as this. So here what I did, I pressed it. From all the sides. I applied force on from all the sides and made it to this side, to this shape, and equal to this. Now I want to make this as this. What is to be done? I will stretch it, and I will make it this way. So until now, how 2 geometrical figures on the basis of their appearance with respect to their shape and size. How 2 geometrical figures based on their appearance with respect to their shape and size, they become similar. We have discussed. So if you stretch it, it will become this. If you squeeze this, it will become this. Or if you squeeze this, it will become this. So if you want to make one figure similar to the other or equal to the other, you can just squeeze it, or you can just expand it. That becomes equal to the other. So this is just for our appearance, based on the appearance of the shape and size of figures, we have discussed the concept of similarity. But mathematically, this is not possible. Mathematically, we need some definitions, we need some concept-oriented mathematical things to understand clearly the concept of similarity. So for that, we have to go a little bit further. Right? So here, 2 figures are said to be similar if they have the same shape and any different size. They are said to be similar. For example, these 2 triangles are similar. How to represent that similarity? If 2 triangles are similar, here triangle ABC is similar to triangle PQR. This is the symbol for similarity. Sir, I don't like it, doesn't look so nice. Okay, no problem. So triangle ABC is similar to triangle PQR. 3 lines which are parallel to each other. Sir, I don't like this. You have some other, no. Sorry, either you have to use this or this. So this is the symbol for similarity, this and this, right? Okay. So for the better understanding of similarity of polygons, we need to understand certain basic concepts related to polygons. So I hope you remember your polygons chapter in your 9th standard or 8th maybe. A polygon is a closed figure: square, rectangle, rhombus, kite, trapeziums, parallelograms, all they are polygons. Triangle is also a polygon. A polygon is a closed figure. Imagine what I am telling you. Go on, imagine. A polygon is a closed figure which is bounded by 3 or more line segments, because a basic polygon is a triangle bounded by 3 line segments, 1, 2, 3 line segments, or 4 or 5 or 6, something like that. Number of sides goes on increasing, right? A polygon is a closed figure bounded by 3 or more line segments which are coplanar. So all the line segments are on the same plane, they are coplanar and they are non-collinear. They are not one beside the other. They have cut, they have bent. So they are coplanar, non-collinear, and the line segments meet each other at their endpoints. See, I will go with the definition. A polygon is a closed figure. See, it is bounded. It's a closed figure bounded by line segments which are coplanar. All the 4 line segments here are on the same plane. Coplanar. They are non-collinear. Non-collinear in the sense they are not like this. First line segment, second, this is third, and this is fourth. No, it's not like that. They are non-collinear. And these line segments meet at their endpoint. So this line segment meets this at its endpoint. This line segments meet this at its endpoint. This line segments meet this at this endpoint. Right? If all these properties apply for a geometrical figure, then we call it as a polygon. So once again I repeat, a polygon is a closed figure bounded by 3 or more line segments which are coplanar, non-collinear, and the line segments meet at their endpoints. And these line segments of the polygon are called the sides of the polygon. They are called the sides of the polygon. Right. So, when do 2 polygons become similar? When do 2 polygons become similar? So, this is a polygon, this is also a polygon. When these 2 polygons become similar? So, if they want to become similar, they should have same shape. So, let us look at the angles. So, this is 90 degrees, this is also 90, this is 90, 90 degrees, 90 degrees, 90 degrees, and 90 degrees and 90 degrees. So, they have to be equiangular. They have to be equiangular. So, if 2 polygons have to be similar, similar means they have the same shape but different size. If 2 polygons have to be similar, that is of equal number of sides. I cannot take a square here and a pentagon here, and I cannot speak about similarity concept. So, if I want to speak the similarity concept of 2 geometrical figures, they should be having the same number of sides. It's understood. So, this figure and this geometrical figure, if they want to be similar, then they have to be first equiangular. They have to be first equiangular. And along with that, compulsory, along with that, if the side is 2 cm, if this is 4 centimeters, so if all the sides are 2 centimeters, this is 4, 4 and 4 centimeters, then if you take the ratio between the corresponding sides, 2:4, 1:2, 2:4, 1:2, 2:4, 1:2 and 2:4, 1:2. So, So what are the conditions for any two polygons to be similar? For any two polygons to be similar, condition number 1, or any two polygons are said to be similar if and only if, this is better, if and only if their corresponding angles are equal. That means they are equiangular. So two polygons are said to be similar if and only if their corresponding angles are equal, that is inside brackets equiangular, and their corresponding sides are proportional. Their corresponding sides are proportional. Proportional means their corresponding sides should be in the same ratio. So this, for this is the corresponding side. Ratio is 1:2. For this side, this is the corresponding side. Ratio is 1:2. For this side, this is the corresponding side. Ratio is 1:2. For this is the corresponding side. Ratio is 1:2. So first condition, they should be equiangular and their corresponding sides should be in the same ratio. If these two conditions apply for a polygon, then we say that those two polygons are similar. Once again, when are two polygons said to be similar? That is the question. Two polygons are said to be similar if and only if their corresponding angles are equal. Second point, their corresponding sides are in proportion or in the same ratio. Both the conditions should satisfy to make two polygons similar. But, these two conditions are not necessary for to prove that two triangles are similar. In order to prove that any two polygons are similar, you have to prove that their corresponding angles are equal and corresponding sides are proportional. But if you want to prove that if any two triangles are similar, then you need not prove both the conditions. You have to prove either their corresponding angles are equal or corresponding sides are proportional. Any one of these two conditions, not both the conditions. Sir, triangle is also a polygon. Squares are also polygons. Rhombuses are also polygons. When both the conditions are required to prove any two polygons to be similar, but for triangle, why not both the conditions are required? Why only one condition is enough? The question raises. Because triangle is also a part of the family of polygons. When the both the rules are getting applied for all the polygons. Triangle says, oh, for me to prove that we are similar, we do not need any both conditions to satisfy. We need any one among them. Question raises, why and how? Right? So, in the next session, I will be discussing why both the conditions are not necessary for any two triangles to prove that they are similar. Only one condition is enough. Why and how? So, in the next session, I will discuss it. So, I hope you enjoyed the entire session of the introduction for similar triangles. Very important chapter. Please watch this video once again if you need it. This is very, very important. Don't ignore. If you ignore this, the next coming chapters of geometry will be a little bit difficult to learn. I hope you enjoyed it. Stay home, stay safe, keep learning. Thank you.